is one of the most fundamental concepts that you can get to when you're talking about dependently typed programming languages. And it's also one of the hardest concepts that you can get to when you're dealing with dependently typed programming languages, because there's so many different meanings of equality, and you have to pick one, right? When it comes down to thinking about a type checker, type checking is all about equality, comparing two types and making sure that they're equal to each other. Every time you type check a function application, you have to check the type, the domain of the function against the type of the argument. And in simple languages, that check is pretty simple. We can use syntactic equality, or maybe we have a slightly more complicated language where we use alpha equality. Or in a dependently typed language, we want to enlarge that definition of equality still and define a new relation that says when are two types equal. And this is hard in a dependently typed language because fundamentally we have computation in our types. And so really what we're doing is we're deciding program equivalence. We're trying to decide these two programs, which happen to compute types, are they equal programs? Right? And that's what we're going to do. And we started talking about this last time, right, when we started talking about what is our definition of equality. Somewhere we need to define, somewhere in our language, we need to define a relation. And I was just writing it A equals B, right? This is the relation that is our equivalence relation. And we talked about what properties we wanted of this relation, right? We wanted it to be an equivalence relation, and we wanted it to be congruent. And that meant if the subterms were equal, then two larger terms were equal that had the same structure. And then we also wanted to make sure that relation contained beta equivalence, that our notion of computation, that if we had some function applied to an argument, it would be equal to the reduction, the substitution of that argument for the parameter. So A with B for X. Now, I'm not going to go into too many details here about what are the possible definitions of equality. We're just going to stick with this one that we have. But I will warn you that there's a lot of other definitions. We could equate more terms. And if we equate more terms, then more things are going to type check. But I will leave that as something that you can go off and explore on your own. So we have this definition of equality. Sometimes you could write it like that if perhaps it needs to know about variables that are in the context. Our definition didn't really care about variables in the context, so I left it off. Right? What do we do with the definition of equality? It's sort of the top level when we're just specifying our type system. We want to think about specifying our type system and adding an extra rule. Right? We want to add a rule that says that if some program in our type system type checks, I'm just specifying, this is not an algorithm, I'm just specifying, if something type checks, then any other type that is equal to the type of that program has that type too. Right? So this is a conversion rule. It allows us to convert types. And notice this rule has no place in an algorithm. When we're trying to use our inference rules to specify a syntax-directed algorithm for type checking, it doesn't tell us where we need to switch types, and it doesn't even tell us what types we need to switch. Right? So here is our first challenge, which is how do we take, so it's very easy to say, let's take our type system. We throw in this extra rule. Now our type system works up to beta equivalence. But how do we implement that? Right? How do we go take our syntax-directed version of their type system, right? The two bidirectional judgments. Gamma shows that A, we can infer the type capital A for little a, and then gamma shows that A, we can check the type of A against this type. How do we take these judgments and add this definition of equality to that? so that when we're type checking with the algorithm that's specified by these rules, we're working up to this beta equivalence. We're implementing the type system that's specified over here. All right, so what do we need to do? What can we do?
If A infers B and checks, A infers A and checks as B.
Yeah, so we need to look at every single rule and think about whether we need to explicitly talk about equivalence, right? So before, when we were writing the system, I wrote a rule that talked about the bridge between checking and inference, right? So there was this rule that said, if we were checking the type of A, but there was no rule that was a checking rule that applied to this form, we could run inference instead, right? But implicitly, this specification is using equality, right? We could have written this rule like this, where we said, go to A, right? We want to check that A has this type. How are we going to do that? Our checking rules don't work. So go to A, infer what type it has, and then make sure those types are equal to each other. Right? So implicitly, when we wrote this, we kind of meant this. Right? And when we go and we implement our algorithm, we actually have to implement this. Right? And if you remember in version 1, when we got to the implementation of this rule, we actually had an alpha equivalence check here. And what we're going to do is we're going to swap out that alpha equivalence check with a much stronger check, something that's going to check these types up to this beta relation. Are there any other places where we have to think about equality in our algorithm, in our specification of these two rules, where we're kind of implicitly relying on equality? Maybe it doesn't jump out at us. Okay, any ideas? Well, let me show you another one, which is our application rule. So if you remember our application, we wrote application as an inference rule. So we're saying our algorithm, if we have an application, how do we type check an application? Well, first we have to infer the type of the argument. And what I wrote last time was I just said infer the type of the argument, and it better look something like that. Right? And if you think about what we implemented last time, what did we do? We called the infer type function recursively, and then we pattern matched on the output. Now, do we want to require that whatever type we infer here for A be syntactically equal to some kind of pi type? Not really. What we want to do is require that whatever type we infer for A be equal, definitionally equal, maybe up to some beta conversions, be definitionally equal to some pi type. And so I'm going to make that a little more explicit when I write these rules. I'm going to rewrite this rule by saying, well, we're going to get some type for A, but then we need some procedure for taking A and finding some pi type that A is equal to. Right? Somewhere, we need an algorithm. It's going to take A, find us a pi type that it's equal to. And then once we've done that, then we can use A1 to check the type of B, right? Because that's the domain type for the function. And then the result type, that's going to be A2 with the substitution. Okay, there was a question. Okay, so this is how I'm revising our rule a little bit just to make the algorithmic calls to equivalence more apparent, right? Where in our rule we're really depending on our definition of equality. Now, is this it? Do we need to do it anywhere else? All right, is this the only two places? It actually turns out there's one other place, but it's kind of subtle, right? Actually, and I'm not even going to write it up as a rule, but in our implementation, we have this idea that we have a module, and what is a module? It's a series of definitions where we say, right, so we might have a module M, right, and then we say X has some type A, and then we give a definition. And what does the type checker do when it sees a module like this, right? It checks this type, makes sure it's a good type, and then it uses this type to check the type of A, right? We're going to call this judgment right here with the type that we provided for the expression, right? Now, if you remember our implementation, when we're checking the type, we just pattern matched. And again, pattern matching is a restriction on that syntax, right? Well, what if we wrote down a type? What if A happened to be some sort of lambda expression, right? Lambda y dot y, right? Now, if we wrote, remember, to type check lambdas, it has to be in checking mode, right? Right? And if we had written down bool arrow bool, we'd be okay. This expression would check against that type. But what if we had written something that wasn't explicitly an arrow type? It was something equal to an arrow type, right? Maybe it's, for some strange reason, we wrote lambda z dot z applied to bool arrow bool, right? Something that wasn't directly an arrow type right away, but after we do a reduction is going to be an arrow type. Now, this is artificial, but it's showing you that even when we start out right away, we're going to have to find, when we do checking, we need to make sure that we're checking up to this notion of beta equivalence. Okay. So those are the three places in that implementation where we need to use our equality algorithm. And I want to make that a little more concrete by actually giving you signatures for the functions that we need in those three places. Right? So if you remember last time, we had our type checker, right? And our type checker, it worked in a type checking monad. And so just like everything else, our equivalence functions are also going to work in that type checking monad, right? And so what we needed, let's see, what up here? We need some way in the type checking monad of telling whether two types are equal to each other, right? And so if you go look at the code, that's actually a function that I am calling, let's see, is this the right, yeah, right? I called it equate. It's in, if you're browsing along or following along in version 2 of the implementation, you'll see there's a function that's called equate, and it has this type, right? It takes two types of terms. Remember, type and term are the same thing, right? And it works in the type checking monad, but doesn't return any interesting result. So what does it do, right? Given these two types, if they are equal to each other, if it decides that they are equal, then everything is fine, it returns unit. If they are not equal to each other, then the type checking monad has error handling capabilities. It's going to trigger a type error, right? And we'll get some error message that says, these two types aren't equal to each other, right? So that's this equate, right? That corresponds to that judgment that I wrote right there, right? So the next thing we need, what else do we need? Well, look at up at the top, right? We can't use equate for our application rule, right? Because we don't know what A1 and A2 are, right? What we need to do is, we know A, right? But we can't just say, well, equate A with the pi type with A1 and A2, because we don't know. We want to find out if there is some A1 and A2 that those two things will be equal to each other. And so what I wrote for that is I had a very special function that was called ensure pi. Right? And that would take a type and make sure that it actually is equal to some pi type, right? And if it is, so if it succeeds, this time instead of returning unit, right, it would actually take apart that type and give me the components of it, right? What do I need up there? I need to know what x is, what a1 is, and what a2 is. So I get a triple with the name for that variable and a1 and a2. Okay? That's 2. And then the last thing, right, for this right here, when the type checker gets started at the very beginning, when we're checking all the declarations and definitions in the module, right, I need one more thing. Right now, here, we could look ahead and say, well, we know it's going to be a lambda, so maybe we should do ensure pi, but actually we're going to be a little bit more general than that, and we're going to be adding more constructs to the language. So when we have, so really what we want to do is we want to make sure that when we call check type, when we call the function that corresponds to our checking judgment, we want to make sure that the type that we're calling it with is actually in weak head normal form. That we've figured out, we've converted it to some form that's equivalent to it, but that we know what its head is, right? Because that's what's important to the type checker, right? We can check a lambda expression when we know that its type, we're checking it against some pi type. And so the last thing I'm going to use is something that's called weak head normal form. So this is a function that's just going to take a type and reduce it to its weak head normal form. So maybe some of you are not so familiar with what the weak head normal form of a type is. So what is it, right? Or how does that differ from just reducing everywhere for the normal form, right? Yeah?
It's when you've evaluated it enough to know its constructor.
Yeah, so weak head normal form, we're just going to reduce it as far as we need to know what it looks like at the top level. So for example, right, something that looks like this, right, lambda x dot x applied to lambda y dot y, right, that's not in normal form. It's not in weak head normal form. That we can reduce this to something else, right? So this is something that we do need to normalize. But what about this guy? Lambda z with this guy inside of it. Now this guy, it's in weak head normal form because we've reduced it enough, right? Or we know what the outermost constructor is. We know at the top level, what is this guy? It's a lambda, right? It's not an application that we can reduce, right? So we don't have, right? We've reduced it to the top level, but we don't have to reduce inside anymore. So full reduction would keep on going and reduce underneath this lambda, whereas weak head normal form reduction would only go as far as the top level. And this is true not just for things that are equal to lambdas, but also, for example, like if we had a pi type, right? You know, if we've reduced it so that we know that, right, so this is a pi type, right? We know its top level form is a pi type, but not all the pieces, right? This domain type, that's not been normalized yet, right? There's still some reductions that we could be doing in the domain type of this pi type. But as far as weak head normal form is concerned, we've reduced it enough. Okay? Right, and in terms of type checking, right, it's that top level form that matters for check type. And then as we keep on going, hopefully we'll make sure we want to have an invariant every time we call the checking routine, that we only call it with things that have had their top, have been reduced with weak head normal form. Okay, so this is how the type system, this typing algorithm in typecheck.hs, how it can use an equality algorithm. But we haven't actually talked to any about how these equality algorithms can be defined in the first place? Right? How do we implement these things? Right? We talked last time, or we just talked now, that we have this relation, right? But just saying it's a relation that contains beta, has symmetry, reflexivity, transitivity, it's congruent, that doesn't tell us how to implement equate. So how should we do it? How can we decide whether two types are beta equivalent to each other? What could our algorithm look like? Right, so do you guys know any algorithms for comparing two expressions for equality? Any ideas? Do you know what Coq does? Do you know what Agda does? Do you know what Idris does? Yeah. Mm-hmm. Yeah? Okay. So here's very simple implementation, right? So here, that's his implementation. We have equate, right? And we want to equate A and B, right? So maybe we have, so you're saying normal forms. So say there is something that instead of weak head normal form goes all the way to normal form, right? So we can compute the normal form of A, right? And so maybe I have some NF function just like weak head normal form but keeps going. And I compute the normal form of B. And then I compare them for alpha equivalence, right? If AEQ in A and B, then what? Return unit, else some error message, right? Blah, 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 blah. These two types are not equal to each other, right? And hopefully they terminate. Again, we're cheating. These things may not terminate. Even if they do terminate, still may take a long time. But there's an algorithm. What do you guys think of that algorithm? Huh? It's too expensive. Why is it too expensive? Okay. Okay. So what you're suggesting is, why do we need to normalize them the whole way, especially if they're not equal, right? There's only one part where they're going to be different. And so maybe we only need to reduce it enough to find the part that they are different from each other, right? Right. So, and that's an idea that is the basis of the algorithm that I've done in version 2. Yeah. Does Haskell's laziness get you? No, because every time you start, alpha equivalence is going to start comparing them all the way. Yeah, it could.
The alpha equivalence procedure in such a way that it will only evaluate, it will only force NA and MB to the degree that it absolutely needs to.
It could.
I think you want error handling because NF might check the weight of 2 variables on 1,000 environment and these check the entire term.
And there is okay, so there's one twist that laziness may or may not help, which I don't know the answer, right? Which is when we're doing, okay, so I described weak head normal form as just doing beta reductions. But there's one other really important thing that weak head normal form does, which is, if you think about our module, right? Our module is this series of declarations and definitions, right? X is this, you know, M is that, R is that, right? And then down here, the types of later things are allowed to refer to things defined earlier, right? Just like when we were encoding AND. We defined what AND was, and then we defined some operations that worked with and had AND appearing in its type, right? Now, when we compute the normal form, right, we can eagerly go through our term and look for all the variables and look up their definitions and eagerly substitute them. Or we could just keep their definitions in the environment and only look up their definitions as we need them, right? If they're in a position where it makes sense, where we might need to know what their definition is. And there I'm not sure how the laziness is going to work with this delayed substitution. And having that delayed substitution around, it's pretty convenient, right? Because a lot of times you don't want to just go through and expand everything out, because when things don't match, your error messages can be really huge, right? Because you've made these names because you have some ideas of some concepts, right? And if things don't match because here at this place they don't match, but then you print it out and there over there's an and, but it's expanded out the definition of and, that could be really hard to read. It makes terms blow up in size, right? So waiting to expand these definitions until the last moment when you have to do that, right? You don't want to expand any definition until you absolutely have to, right? That's going to really help the readability of our error messages. And also might help the efficiency of our algorithm too. Now, if we were implementing this in OCaml, for example, and we didn't have Haskell's laziness around, right? We also would want to think about how we would make sure that we could interleave the equality checking with the normalization, instead of trying to do all the normalization at once and then checking for equality, right? And so that's what the code in the module equal.hs does. The actual definition of equate, what does it do, right? It checks to see whether the two things already are equal, because you might as well do some check right away. And then it just weakhead normalizes them and then compares their top levels, right? And when it's comparing their top levels, as long as the top levels match, then it can call itself recursively and only then normalize the subcomponents, right? And if it finds the top levels don't match, it can stop normalizing. It doesn't have to normalize all the way. Yeah.
So the native fusion, that makes sense to me why that's important.
Yeah.
Being quicker in the case of a mismatch seems to be a no.
Yeah.
Trivial to me, because can I get 99% of all the aspects to be add-on zero, I can add up, and
That's true. That's true. Okay, so finding a mismatch, but what if two things are already equal, but they're not in normal form? That's something that we can find quickly.
Yeah, as I say, that
Yeah.
fusion makes sense,
Yeah.
but
Yeah.
it might be for the case where
Yeah.
you get a time error, seems to be a bad
But sort of interleaving, checking the top levels with normalizing also gives us a chance to check to see if we've normalized enough for equivalence. Maybe we had to do a little bit of normalization, but much of the term is already equal to each other, right? And that will allow that to cut in. Yeah?
Too much and like prematurely, like we shouldn't have normalized this as far as we did already. Does that ever become a problem?
If this language, everything terminated, there would be no risk, right? If we had the property that this language was strongly normalized, that would mean that everything that's equal would all come down to some same form, right? That would be the right? And languages like Coq and Ag that have this property, right? So you can't do too much, right? I mean, you're only paying in time, right? In the end, it will come down to the same thing. They'll be equal to each other, right? Even if they maybe they join earlier, and hopefully we can cut out early because they join earlier. But once they're the same, they're going to be the same.
Another question, do you always know on which side you have to go deeper? When you compare?
So you're going to go deeper on both sides, right? Because you're going to make sure they have the same top level structure, right? And maybe you have to do more work on one side or the other to get to that top level structure, but weakhead normal form, that this algorithm for computing the weakhead normal form, it will do all that work. It will do as much as necessary. So it doesn't really need to be smart about that. Yeah?
So this doesn't tell us that like quicksort is equal to bubble sort.
This does not tell us that quicksort. Well, okay, so what you're asking about, I will rephrase your question. Right, so what you're asking about is, what about this rule for equality? Right, lambda x a x equal to a, with the side condition that x is not in free variable. to include ADO equivalence in our definition, we have to include it in our algorithm, right? We have to adjust our algorithm to implement it as well. And our particular algorithm for equate is not going to do that. Right? But there are algorithms. And those algorithms typically take the types of the things that we're comparing into account to help figure out how to compare things to ADO equivalence. But I'm not going to go into that. Okay, so
I'm not going to go into as much detail about the implementation of definitional equivalence other than sort of giving you a high-level picture of how it works, right? And the reason is I want to also get into I want to talk a little bit more, I want to go back to our typing rules and talk a little bit about how once we are enhancing our definition of equivalence, maybe we should reconsider some of the typing rules that we've defined in our language. All right, so let's think about the homework assignment for a little bit. Right, so who thought about bidirectional rules for if? Right, did anybody think about this? A couple of you asked me about it. Right, so I want to talk a little bit about what those bidirectional rules for if might look like, and in general, what typing rules for if in a dependently typed programming language might look like. Let's see here. I think I'm going to just erase this board. Right, so I gave you some rules. I gave you a specification of if. And what I did is I asked you to think about how you might turn it into bidirectional rules and how you might implement it in this little toy programming language that we have. Right, so the specification I gave you, right, it was not too complicated. It said the bool is a type. It said that true and false were booleans. Right, I won't write false down. And then it said if expressions type check if the first part of the if was a boolean and the second two parts have the same type. Okay? Okay, so how do we turn this into an algorithm? Right? How are we going to do checking or inference, right, in this system? Right? So what should we do with this rule? How could we redefine it? Yeah? Yeah, it's an easy inference rule, right? We can say gamma shows that bool infers to type, right? It's pretty direct, right? And the same is true for true. Right? True. We easily look at true and know that it's a boolean. What about if, though? Right? Should we check, in the end, in the bottom, right, should it be if A, then B, else C? Should we do inference or checking here? Do we need to know the type of the if or not? Yeah. We could do both. Okay, let's talk about inference first. What if we wanted to do inference? We wanted to infer the type. What would we do? What do we need to do to infer? Yeah? Yeah, so if A is a bool, right, we could infer the type of B and C, right? So A, I'll do A1, A2, make sure that they are the same. Right, and if they are the same, it doesn't matter which one we return. Right? So that's inference mode. Right? Yeah, so now notice here, what if we had written it like this? That's completely equivalent to like inferring them both and checking. Well, not completely equivalent because it allows, if C is a lambda, then you don't need an annotation there. Slightly more expressive, but it works too, right? So we can do that, and that's still inference mode. What about checking mode? right? Somebody said to us, make sure that this expression has this type. Then what would we do?
One question regarding the other one.
Yeah.
You said now it's slightly more expensive because C could be lambda.
Yeah.
Should we also try to cover the other case where B is a lambda but C is not?
Okay, so we could, yeah, so,
B phase, we could try to insert C and then check that with B.
yeah, so what you're saying is, let's have two rules. This rule is asymmetric, right? So we could also equivalently, or at the same time, have the other rule that first infers C and then checks B, right? And that would at least make things a little bit more uniform. Yeah. What about checking? Right, still check that A is a Boolean. And then here, now we're giving A, it's completely symmetric. We can just check B and C with that type that we've been provided. Okay? Okay, any questions about these rules, right? And it's kind of neat how if kind of works both directions, right? If we're in inference mode, we can pull the type out. If we're in checking mode, we can push the type down. But now I want to make one change to this rule, right? And this change comes about because we're working in a dependently typed language, right? And I want to make it slightly more expressive so that when we're type checking our if expression, the type checker should know something about A, right? So when we're type checking B, I'd like it so that the type checker knows that A was true. And then when we type check C, I'd like the type checker to know that A was false, right? So let me just show you a simple example of a program that needs that kind of rule, and then we'll talk about how we'll even express that rule, both as a specification and how we might implement it in an algorithm. So let me first start off with an example. And again, this example, it's just trying to capture the idea. It's not trying to be realistic or anything. All right, so say we have T, and T is a function from Booleans to types, right? And so T is going to be lambda B, right? If B, then, right? And if B is true, then it will return the type bool. And if B is false, what's another type? Let's pretend we have unit, right? So I'm gonna call unit 1 in this language, right? And now this one type checks with our plain if rule. We don't need anything fancy to type check this. But say we have this definition, right? Right, so what is this going to be, right? So this is going to be a function that takes a Boolean, has a dependent type, and its result type is going to be determined by T. Okay? Right, so this is going to be the type of X. Now what could we do to implement X? Right, so X is going to be it's going to take some Boolean argument. Right? And if B is true, then what should it return? False or true, right? It's got to return some Boolean value. Right? So false, that sounds great. And if B is false, then it must return unit. Right? I'm going to write unit as TT. All right, so this guy, we can't type check with that rule, right? What is A, right? It's just T of B, but false isn't T of B. False is bool, and T applied to B, where B is just some abstract variable. That's not equal to bool. That's only equal to bool when we know that this guy is true, right? If we knew that variable, if we knew B were true, then we could reduce T and know that the type that we need is bool, right? But we have to tell the type checker that in this case, we know we would only be in this case if this guy, this argument, was equal to true. And likewise, we would only be in this case if this argument is equal to false. Right? And that's a really powerful idea. But how are we going to express that when we're thinking about our type system, and how we're going to implement that when we're implementing our type system? All right, so let's just think about expressing it. How could we modify this rule, this specification of if, so that we can type check that program there? Yeah? Add something to the context for checking B and C. What do I need to add to the context, or what? Right? Something about the value of A. Right? Somehow, when I type check here, I need to know that A is equal to true. How can I tell that to the type system? I could substitute. I can use substitution, right? Because substitution is really talking about equality, right? When you substitute one thing for something else, you're saying these two things are equal to each other, right? What if I say, instead of writing A down here, I say, we have some type A, and somewhere in that type, right, A, we can kind of think of this context with some X, and somewhere in that context there's an A, right? And over here, we can change out that A with true, because here we know A is true. And over here, we know A is false. Right? This is a little bit hard to think about because just writing the rule this way doesn't tell you at all how to implement it. Right? But what it's doing is it's sort of saying, you know, something about it. What is A in this example? In this example, capital A is just T applied to X, and then we're going to substitute B for X in the result type. Then here in this branch, we're going to type check that branch where it's T applied to true, which reduces to bool, so that's going to work. And over here, it's going to be T applied to false, and that's going to work. Right, so this is a way of specifying. Now, this is not the only way of specifying this rule. There are plenty of equivalent specifications. Because remember, we have an expressive equality now, and so we could have also written this substitution as an application. Right, so another way we could have written this rule, is actually require that A be a function that needs a bool. Let's see here. Bool needs a Boolean to give us the result type. And in that case, we can also write this as just applying A to true, false, and A, right? And that's completely equivalent, right? Because remember, we're working up to beta equivalence, right? If A is some function, it's just going to reduce. That function's going to have an X, some argument. We're going to beta substitute. Okay. That's the specification of the rule that we want. How do we implement it? Any ideas how we might implement? Why is that hard to implement? Yeah. Yeah, ask the programmer to do it, right? Make the programmer give us the A function. And notice, we can't get the A function from here, right? Because here we get a type, right? We don't get a function, right? So if the programmer is going to give us the A function, then it has to actually somehow be annotated on our term, right? And if they annotate that A function, and then we could infer that the result is A applied to A, and then here we could do true, and here these actually can both be checking now because the programmer gave it to us, right? So we know that that has to be A true, and that has to be A false, right? So one solution is just require the programmer to give it to us, that A function. Is there another solution? Yeah?
Well, we could infer the type of A and B, and then of B and C, and then our type would just be the function then. If A equals true, then return the type of B, and if A equals a positive between type of B.
Okay, let's see here. Let me write that down. Right, yeah, so, right, so we infer this and then get A. Oops, no, that's not. Yeah, this has a, sorry. We start with A as a Boolean. Right. Start with B, we get A1. We start with C, we get A2. And then, to infer if A, then B, else C, what do we infer as the type? If A, then A1, else A2. Yes. That's another way we could do it. It seems really crazy, doesn't it? Right? It does, right? The type, if we're trying to type check an if, well, it's an if. Then how do we type check this if? Right? Well, hopefully, eventually, it's not dependent anymore, right? And something goes away, or this, or we know what that is, right? So that's another alternative. That's not what I did, right? I did yet another version. It'd be fun to try to implement this and see what happens, right? Right? I did another version, right? And the other version that I did was, again, I like to cheat. So I cheated, and I said, the problem with this guy, the programmer, giving us A, right, when we're checking, right, is we needed a function, right? We don't know what X is, right? You know. So what if we write a special rule that only triggers when our scrutiny, when we're doing an if on X, right? So back to this one, right? This was A applied to X, or just A with a substitution of A for X. But then there was X, right? So we know what X is, right? And so that means here, when we go down, we can still keep checking, but now we can say X is true and X is false. Right? But again, this only works when we're looking at something, when it's a variable, when we have something we can substitute for. Right? This is a way we can tell the type checker that we know. For arbitrary terms, it's hard to tell the type checker that an arbitrary term is equal to true. But it's very easy for us to tell the type checker that a variable is equal to true. We have substitution for that. Or even actually, we could throw it into the context as a delayed substitution. We don't even have to do it immediately. Right? And so that's what I do. Right? And that works for this example. Right? But of course, there are many examples where this won't work if, for example, this is not a variable here. Okay? Now, we could do something similar to this for sigma types, but in interest of time, I'm going to not do that. If you want, you can view that as an exercise to work on during the hands-on session. And if you want to see how you can add, change the elimination rule for sigma types so that it gives us this dependent elimination, I can also help you with that during the hands-on session. Okay, so the next thing I want to do is talk about, so we've talked a little bit about definitional equality. Now I want to add something new to our type system, which is propositional equality. All right, so we have this language, and we started with only 5 things, right? With just functions and type and variables and application, right? In your homework, you added Booleans and sigma types. I want to make a new addition now, right? I want to add a new type that's an equality type. And you've already seen this type before, right? You've seen it in Calc. You use it almost every time you use Calc. All through Software Foundations, it's all in there, right? So what is it? And definitely our language should have it too. Okay, so I'm just going to move this board up. Maybe I'll move this one down. All right, so what is an equality type? But what I'm doing is we're going to extend our language with a few new syntactic forms and then talk about what the specification of the type checker is for those syntactic forms, and then talk about how we might implement the type checker with those new syntactic forms, right? And so that new syntactic form is the equality type. Now, let me just prove that you've seen it before in Calc, right? So whenever you see something in Calc, it looks like this, right? Theorem, right? I've pulled this right out of Software Foundations. Plus 0 in, right? And what does it say? It says for all in colon nat 0 plus n equals n, right? That seems like a perfectly reasonable theorem to prove in Calc, right? But you know in Calc that propositions like this are types, right? And so that means that this part, right, so that's the for all. That for all is pi, that we already have that in pi for all, right? Now I want to add this guy, this equality type to pi for all, so that we can state things that look like this. And we could talk about equalities between expressions, right? So what does that mean? What do we need to add to pi for all to be able to talk about equality within the language, right? So in our syntax, right? So remember we have our abstract syntax in the language, variables, lambdas, application, pi, type, right? We're going to add a new type form that's called, that is equality. Two things are equal to each other. Could be lowercase a, could be capital A. Doesn't really matter. This term is equal to that term. Right? That's a new type. We're going to have a new introduction form for that type, which I'm going to call REFL. Right? And we have a new elimination form, which I don't have enough board space, so I won't write it down yet. Okay. So what does it mean? What is it? So essentially what it boils down to for propositional equality is that if we have two things that are definitionally equal, and maybe I won't put the context there, right? Two terms that are our definition of what equality means, says these things are equal, they're beta convertible, then REFL is a proof that they are equal, of that proposition, right? Then it's true. Yes?
Parameterized by the types of A and B? We just have one equality type?
I'm jumping ahead. I didn't tell you how the equality type, it is parameterized by the types of A and B. I'm just not writing it down. Yeah. Right. So let me actually write that down, right, and show you the rule that shows you when is A equals B a type, right? And that is the case when A has type A and B also has type A. So both sides have it. I'm just not writing down.
Capital A. You can get it by looking at the types of lowercase a and b. Yeah?
So no heterogeneous equality?
No heterogeneous equality. Again, many ways to do equality, independently typed languages. I will not do them all in these lectures. Yeah?
The equal sign on of the first rule.
Yeah.
That is not the equality type, correct?
No.
That is a relation expressing beta equality between
Yes.
A and B.
Yes.
And then the one on the next line is the
Yes.
actual equality
Yeah,
type.
yeah. So we're connecting these two different judgments together, right? We have a judgment for type check, that's this one. And we have a judgment for when things are equal to each other, and that's this one. Right? And notice, another way to write this rule, right? I could have also written this rule like this.
Right? Is that right? And that looks a little bit, that makes it more sense why we're calling it REFL. But it turns out that This one is going to be equivalent, and actually I should be checking to make sure that A and B are well formed, but I'm not. These two rules are equivalent to each other. Why? Because given definitional equality, this type, knowing that A is definitionally equal to B, this type should be equal to that type, right? We wouldn't want those two types to be different from each other because A is equal to B, right? And so, again, we want definitional equality to be a congruence, and so it should be a congruence even through the equality type. So two equality types are going to be equal when their subcomponents are equal, right? So A is equal to A, and then we also know that B is equal to A, but just that's the symmetric version of this one, right? So these are equal types, so this is equal ways of stating this rule, right? But this version of the rule kind of makes it clear, what is this equality type doing? It's taking this judgment, this definition of equality, and it's reflecting it into the type system. Okay, so that's how we prove things are equal to each other, right, using REFL. How do we eliminate it? Right? What do we do with equalities in Coq, for example? Right? Or in Coq, when you are using a proof of equality, what sort of term gets generated? Yeah.
The way we use an equality is when we rewrite
Yeah.
to another. So when we have A equal to B, what we usually do is remove all terms that equal and substitute for that.
Yeah. Yeah. So we use it for rewriting, for replacing A's with B's, right? And so what we need is an elimination form that allows us to do it, right? And actually I'm going to call that elimination form subst, because he said we're substituting all the A's with B's. So let me write down the rule for that elimination form, right? And I'm just making up a syntax for it, because there's lots of different ways you can write it. Coq uses pattern matching for this syntax. It's a little bit different. So I'm going to give it a little bit different algorithm, so I'm going to give it a little bit different syntax, right? So if we have, so we have A, and we have B, which is a proof of equality between two things, A1 and A2. And then A, right, has some type with an A1 for X in it, right? Somewhere in little a's type is a context. Somewhere there's some A1 that appears. And what we want to do is the result of doing this subst is change that A1 into A2 for X. Right? We want to replace this guy with what we know to be equal to it. So how are we going to implement this rule? Well, how are we going to implement this, and that in our bidirectional type system? Right? How do we extend our algorithm so that we have all of these available to us? All right. Let's take just the type itself first. All right, what if we have right? Can we infer its type? Should we check its type? We can infer its type. We know what type the equality type has. It's a type, so we should infer that as type. Right? When should we infer that the equality type is a type? All right, well, we need to know the types of A and B, right? We need to know that A and B are well formed, right? And, right? But we don't know what their types are, right? So we could write it like this. A has type A, B, we infer the types of A and B, make sure they're equal to each other, just like we did for if. We could also thread the type of one to the other if we wanted to, and do it symmetrically if we wanted to. Either way. What about REFL? How should we add REFL to our algorithm? Right? Should we infer its type or should we check its type? Require somebody to provide the type for us? How would you ever infer it, right? Yeah. We know it's going to be some equality type, but which one? Right? We can say, well, you know, always infer that true is equal to true, right? But that's not going to get us very far, right? So we can't infer that type. So we have to check that, right? Right? And I'm going to write it like this, right? We're going to, because our algorithm is written so that we're kind of expecting everything that we're checking to be in weak head normal form, right? So we know it's some equality type, but we haven't normalized A and B at all. So we're not necessarily going to require that they are going to be syntactically equal to each other. We're just going to require that we can equate them, that our equality algorithm will return yes for those two. All right, and so that's for REFL. That's when REFL should type check. Right, now, if we wanted to infer the type for REFL, we would have to put an annotation. Right? If somebody had written down for us that we're going to REFL A equals B, then we could infer its type. Right? And when we do our elaborator, it's actually going to take the type that we check it and put it on the term that is produced so that we can always infer that type. Okay, last one, subst. Yeah, yeah.
Make this section on the right hand side, the check dependent, polymorphically dependent on types, and generalize it over all equalities, make it for all types that are equal.
I'm sorry, which rule are you asking about?
This one on the right.
REFL or subst?
No, this one.
REFL, yeah.
So we can use dependent types in this, right?
Yeah.
So we could modify over those types.
Right, we can say REFL has type what? X, A, Y, A, arrow. We wouldn't want to just say that, right? Because that would allow us to do everything.
Yeah.
Right, that's clearly not a thing. Right. So, and I don't really know how to make the restrictions. Well, you can say only if they're equal. That doesn't count either. Right. So we do really have to make this determinate. Right. We can't just use our other. That's a really good question to ask. Can we use other language features to help us simplify our system? Right. And express something in terms of other things. But in this case, it's not going to work well. Okay. What about subs?
I have a question.
Yeah.
In the REFL case, why do we need to check that A equals to B?
Oh, why do we need to check the A equals to B?
Yes.
Right. So you could be asking two things.
Yes, I guess maybe A equals to B, this formula, just type check it. That might. Oh, we really need A equals to prove A equals to B.
Right, so you're saying why not have this instead? Right, so this is something different.
Right,
What
right,
I
right,
arrayed. Right, and this doesn't ensure that A is equal to B, right? So
right.
this would allow us to show that REFL shows that true equals false. Because true and false are equivalents. And that's all that this requires, is that the two things have the same type. Right, so true equals false is a valid equality type, but we're never going to be, we should never be able to say that REFL has type true equals false. Right, so that's why we need to make this restriction that REFL this function.
Back to one more question. Yeah, definitely. No, definitely. Thanks for all these questions.
So this equality type you have is you're essentially you're saying that the types are equal, right? This is what your reflection is trying to say, right?
Yeah. When we have A equals B, we're saying these two things are equal.
Right. So, and the problem we were just talking about was we have to make this a primitive because we need one for all types that are equal. Right? Is it what you were saying? Well, so I guess my confusion is the same.
Yeah.
I was under the impression that you could simulate polymorphism using different types, and if you can do that, it seems like we should be able to have some kind of write something that says under these conditions the types are equal.
So.
Well, maybe what I'm
No.
asking.
There's a long answer to your question.
Okay.
Right. What you're asking is, does this need to be primitive, right? Especially because with your, I don't know if you talked about this with Koch, but the equality of type is something that's defined in Koch, right? There's a definition that says inductive data type that is equality, and it says it has a single constructor that's regretful, right? But you still have to have that structure of being able to define inductive data types to be able to define equality, right? We don't have that. Now, you can use polymorphism like a church encoding to get a limited form of equality, but which actually, as far as we've gotten here, but I'm about to make equality a little bit more expressive than this, and there the church encoding won't be able to handle it. Right? And I can talk to you more about this if you want to see what the church encoding looks like, I can talk to you during the session. Okay. We want to implement.
Right, we want to add subs to our type checker. How can we do that? Right, again, right, we have subs. A by B, right? Are we going to do inference? Are we going to do checking? Perhaps, what are we going to do with A? What are we going to do with B? Right? Most likely for B, we're going to infer that it happens to be an equality type. We have there's no way we could know what equality type we're trying to switch around here, right? So let's infer that B is A1 equals A2. What could we do for our algorithm? Any ideas how we could implement this? Yeah?
You want to check that A has type A1 or A2.
A has type what? A1 or A2?
Well, I guess it depends if you want your
oh, yeah.
rewriting to be allowed to be bidirectional, right?
We're going to do the same direction here, right? That's the rule we're trying to implement. Something that gives us something like that one.
Okay.
Right.
So then you need to check to see that A is
Right, something like that. Right? But then where does A come from? We could annotate it. Right, because it can't be this A, right? Because we also need to do the substitution here. Right.
Would you like substitute X for A2 and then substitute A1 for X to go backward from the final type back to
Oh.
for A?
Are you saying this could be, yeah, that could be inference because we've annotated here, right?
Oh,
and
no,
we have
I'm
that
sorry.
substitution.
I'm
Yeah.
the other direction.
Yeah.
Sorry.
Yeah, so we can, right, so that works if we're willing to put that A there, right? You know, it's actually a function, right? You know, if we're willing to write that down on text. What if we didn't want to write it down? Can we do the same kind of hack that I did for if? Right, I did a hack for if. In a certain case, we could use the checking rules to tell us what A was for if. right? And that certain case was if we happen to be, right, if one of these guys was a variable, right? So if we have subst A by B, and B wasn't an arbitrary equation, but it was, we want this to be x, so that's B is A1 equals x, then we could just get A there, and then we can push that A down in this type A after a substitution. And push it down. So that would be a way that we could have subst without having any kind of annotation whatsoever. Right. Or we could just ask the programmer to give it to us to give us a much more flexible rule. And we could also add the symmetric version. If it was x here and A1 over there, that would be fine too. Yeah. You mean here? I don't know how you define that operation, right? I only know how to define the operation for substituting for variables. Right? I mean, it would be great if we could make it more expressive and find some other term here that we could substitute for, but I don't know how to do that. Oh, you're saying, I'm sorry, I'm not sure what you're suggesting then. Oh, if you look in A and you literally see an A2 and you replace it with A1. Yeah. There may be a way that you could define that operation. Right. It's a little tricky. I mean, I haven't seen that too much, but yeah.
In the by inequality, and say rewrite using
Yeah. Yeah, I think, maybe we could do that, right? Where we would just always have to replace every occurrence of A1 by, or every occurrence of A2 by A1. Right. And we could find those because we would be finding all of the A1s. That maybe, that's still, we would need that. Anyway, something to think about. Yeah.
So you've referred to this as a hack when you did it for if and
Yeah.
when you did it here. Do you know something we don't about how expressions end up being written as why it's reasonable to do the hack?
Yeah, I mean, well, if you think about it, a lot of times it is a variable there, or at least for if, right? A lot of times it is a variable, and if it's not a variable, you can use a let to make it a variable.
Okay.
But in terms of how well this hack works, right, you have the tool to investigate that. You can take version 2 and write some version 2. Okay.
More tweak, right? And that is going back to this rule here and making this rule more expressive, and then trying to implement the revised version, right? Because we can actually do better than this definition, this typing rule for subst. What do I mean by that, right? Well, I didn't really tell you what the beta rule for subst is, but in our normalization, we want to be able to get rid of these subst terms sometimes. And when are we able to get rid of them? It's when the thing that this proof here, right, when it's already obvious that these things are equal to each other, right? When we know already that A1 and A2 are equal, then we don't really have to do a subst, right? And when do we know that? We know that when REFL can prove that, right? So our reduction rule for subst is, right, subst A by REFL actually reduces to A, right? If our proof here was REFL, then we know that A1 and A2 are already definitionally equal, right? So there was no need to do the subst in the first place. Because if they are definitionally equal, then this type and that type is also definitionally equal, right? That was true from our definition of equality. Now, what that means is that when we start evaluating A, right, we know that B should be equal to REFL, right? So we should, when we're type checking A, let it know about that, right? So here we have one substitution to talk about this equality, but I'm going to add another substitution that says that we know B, here A can have some references to B, and up here, when we type check A, instead of using B, we'll use REFL instead. Right? It's not just any arbitrary proof of equality we have. It actually is REFL. Right, and this is going to give us an even more powerful elimination form. So just like, it's very similar to when we had if, right? And we were letting the then branch and the else branch know that the thing we were looking at was true or false. Here, we know if we can eliminate a subst, we know that we must have a REFL there. And we're increasing that knowledge. Right, and now how do we implement that? Well, you could do a similar hack. You could do a similar hack, you can annotate, all of the same techniques that we've just been talking about. Now, I'm running out of time, so I want to talk a little bit about homework for the hands-on session. I mentioned a few things just now while we were talking, but I do have a homework file that is some programming in Pi for All. If you want to play around with the system that has these hacks for these rules, right, and it has propositional equality, and you can start using that to prove things. So if you look in the file, it's version 2, test, homework 2.py, right? It has some trust me's in it, and you could try to take a look and see if you can fill in those trust me's using these structures that we've just been talking about how they're implemented. You can also take a look at the type check file in version 2 to see how these rules that we've been writing on the whiteboard, how they translate to the actual code themselves, how we've implemented them. Okay. Are there any more questions about equality? Right? You will hear lots more about equality later on during the summer school, but this should give you kind of an introduction. And if you do look at homework 2, it's going to ask you to prove some things about this propositional equality type.